Hello, everybody. Welcome back to the Enterprise Universe. Today, we're actually going to continue our discussions with Dr. James Stoker about world climate mapping. And in our previous session 1 on the world climate mapping, we were taking Ireland as a use case for discussing how the world climate mapping could actually make a big difference to small countries like Ireland, and by extension to very large countries like the US or India or China. So today we're going to continue those discussions, and maybe we can start off by just bringing viewers up to speed. World climate mapping is a new concept that's been developed by Dr. James Stoker, and maybe we can have a quick overview of what world climate mapping is, Dr. Stoker, and then maybe we can continue on talking about how world climate mapping can be applied at the country level, for example, in the Irish context.
That sounds great, Eamon. I appreciate that. And in fact, we covered so much ground in the last segment. I feel like some of those points need to be beefed up a little bit and dug into in the background. So I would do that. We're still going to continue the role playing that you were generously playing as the chief of the Division of Natural Resources for Ireland. So, just a quick question for you. Mm-hmm. Given what we discussed as the chief of this division, do you have any questions, or what are your thoughts about what you heard so far?
One of the things that came to my mind was that when I thought about the entities like NOAA, for example, which is the National Oceanic and Atmospheric Administration here in the US, those organizations provide, I guess, climate-related types of services, but they seem to be different to what the kind of services that we're talking about in terms of world mapping. And I just thought that might be a good area kind of to discuss how maybe talk a little bit about NOAA and the type of services they offer versus what the kind of the climate world climate mapping is, and then just talk a bit about how it's different than these more traditional type of atmospheric services that governments have engaged with in the past. So could you talk a little bit about how world climate mapping differentiates a little bit from like a NOAA type entity? And I know certainly Ireland doesn't have a NOAA type entity, but certainly the UK has got its Met Office, and then you've got NOAA, and then I'm sure India and China have similar, and Russia have similar type of organizations. So could we talk about why world mapping is going beyond the type of services that those entities currently provide?
I think that's a great question, Eamon. So I'm switching you back and forth from the chief division chief and this one. This one, I'm thinking it's more of a general question. Yes. Yes. So essentially, NOAA's forecasting system, and also the European Center model, they produce long-term forecasts also. Yes. For projections in the next month or next 6 months, and even a year or even longer. But the deficiency in any of those products is the resolution. The resolution is coarse enough that you will not be able to resolve any of the physical processes I talk about, because those methods are not really trying to capture the underlying physical processes. So I'll give you a concrete example so you would know. If any of these organizations gave you a 6-month forecast, let's say a 40-kilometer resolution or 50 or even 55-kilometer resolution. So you're talking about a box, horizontally speaking, 55 kilometers on one side, and another 55 kilometers on the other side. That's the box. So compare that to the box that I have been using, the 1 kilometer resolution. So there are lots of boxes within that.
Well, there's 2,500 boxes.
Exactly.
You've got it's not one order of magnitude. It's actually the cube, actually. So it's 50 times 50 times 50 times. So I don't know what 50, whether it's like it's
The
tens of
horizontal
thousands.
vertical resolution is also coarser,
Right.
but that's just one point. The other point is, even though the resolution is higher, I'm also using the process enabling capability. That's what separates the Stalker method from other modeling exercises where they may be using higher resolution, but they still don't have the Stalker method to enable the underlying physical processes. So there are maps available, as I pointed out last time. It's just that they're not reliable because of the amount of information that's going into those models. So it's really not a novel concept when it comes to actually mapping the world, but mapping the world with more information by enabling the underlying physical processes. That's where the difference is. That's where the accuracy and the consistency and the robustness of the maps that come out for individual countries as well as for the globe.
And it allows, like, and I think this is really important for the viewers to understand, is that the ultimately there's a big difference between the physical process driven model versus the learning model type of approach. And I certainly have seen that in the utility industry, because we obviously do load forecasting, and a lot of it is the learning approach, which is okay as long as you're in a steady state and things are changing gradually. But it really doesn't serve you very well, number one, when you want to get to a fine grain level, which is like what's happening at a neighborhood type of level. And then number two, it doesn't help you a whole lot if things are changing rather rapidly. Would you say that you've got the same kind of a problem, that there's the resolution and the dynamic nature of the climate makes the NOAA and the European methods fundamentally, not only coarser grained, but frankly, they won't respond as well to changes in the underlying physics, the drivers of the underlying physics. Is that a fair statement?
It is a fair statement, because you are unable to capture physical processes of relevance at that coarse resolution. That's the first thing. But remember, Eamon, the Stalker method is really about pointing out or realizing the deficiency in the science itself. So this is really not about the approaches that they're using. They're using the approaches that are allowed in the science as we know it. So the Stalker method is about the realization of what's deficient in them and how to overcome that. That's really how I came up with the process enabling capability.
Right, and that was because, like, if I understand it, so if I'm the customer here, and I'm saying, well, Dr. Stalker, how come we've got NOAA here and it's got its billions of dollars and they're stuck in their paradigm. You've been working on this for 20 plus years, integrating all of these different physical processes into your model since the time you were at Sandia Labs, I presume. Why now? Why didn't this come out 5 years ago? Like, why is it because it's taken this long to, I guess what I'm trying to understand is, if I'm the cynical buyer, I can say, well, Dr. Stalker, why is it taking so long for us to get this service to market, and why is it, and also, okay, if this is a global service like that, am I going to have a NOAA type budget in order to buy this service off you? Billions of dollars a year.
You asked a lot of questions there.
Sorry.
No, let me unpack one at a time. So the bottom line is, there are three things about the Stalker method. First thing, realization of the deficiency in the science, in the computational fluid dynamics, which really did not take me that much time. It's only a few months. Then actually making the method based on the realization and what to do. That took me probably another 6 months to really gel it all together, in addition to realizing it. But what took me the longest time, Eamon, implementing that into a model and then validating it for various applications. Because as a scientist, I mean, I'm still a scientist. I want to know, everything about what I do and making sure everything is addressed. So I was doing that even though I was a businessman, trying to make some contracts and things like that. But as I pointed out before, without my satisfaction of the products and if they're going to be good for my clients or not, I wasn't going to release them, even if I were able to make some money. So to answer your question directly, it took me a long time to apply it to various areas and then validate them to my satisfaction. So that took many years.
Yes.
But the other thing too, Eamon, the challenge has been when you are trying to come up with a computationally intensive, costly product compared to other products that are out there. They're actually in the public domain, which is really like free. So you are really not really free. Indirectly, it's not. But so you're talking about that dichotomy that I had to overcome. So there are lots of issues. There are lots of vendors massaging public domain data, not really creating a lot of value, which I pointed out so many times. But I really had to take my time to actually get it all together and get the market message. Now the publication and also the presentation at Boston University. So a lot of factors really went into it. And as far as the budget, let me answer the budget issue too. So here is what I think. When I'm able to create the benefit, okay, so let's say that's 100 units, and the current methods using the 10% data, they are never going to be able to create that 100%, 100 units of benefit. They're going to be much lower than the 100 units. Even if you give them more money, they're not going to be able to get you to 100 units of benefit. So I'm not really talking about competing with these methods and their price points. So my budget is going to be higher, there's no doubt, but the benefit is going to be so much higher. It's the wrong end to think about when it comes to global mapping using the Stalker method.
So I just want to then just repeat that for the layperson. So the method is based on computational fluid dynamics with all the physics built into it. It has been validated with use cases. So it essentially, you've taken the science and you've turned it into an invention. And I think there's one thing having the formulas written down on a piece of paper. There's another thing actually having the invention in place. And yes, and then the third part is the invention needed to be computationally feasible, if you will. So you had to work through all of the issues of integrating the public data, making sure that the invention actually worked, testing the algorithms to make sure that you had actually gotten them right and that there weren't errors and bugs in there. So we are ready now. I guess the point is that the engine, the invention is now finally ready, and that it is capable of operating at country and continent and even global scales. And I guess that's what I just wanted to just validate. And my role as the Irish guy here, that it's ready to be rolled out as a service for the use cases that we've talked about in the last. In other words, this isn't a theoretical discussion like many have, like science fiction. We're talking about an invention that is based on a new way of as you said, a computational physics-based engine that has been validated over a number of years, that's now ready to roll out as a service for countries and even continents to deal with some of the most pressing use cases that we face today. That is a true statement, correct?
It is absolutely a true statement. In fact, the biggest application of this technology would be to ascertain climate change. And I think I'll go over that a little bit more. But think about the three phases of the development: realization, and the method development, and the implementation. Implementation took a long time because I needed to apply that to various applications. Renewable energy was where I started, with wind first, and then solar radiation, and then weather options forecasting in temperature and precipitation. So these are some of the things that I added on, even though when I was doing wind, Eamon, as I was telling you before, I had to do all of the other processes related to solar radiation and temperature and other things because
Yes.
my comprehensive approach does not allow me to do just wind for wind or solar radiation for solar radiation because that's not how the atmosphere works. And that's why, you have to think about 2 months, 6 to 8 months for phase two, and several years for phase three in the implementation
And
stage.
these are non-trivial physical processes like the process of cloud formation. I would imagine is just that alone is not a trivial thing to model in the atmosphere, given that it occurs at different altitudes and it's a function of various, so I'm sure like getting these, integrating all these various physical processes, and that's why I think the hardest part of your invention, actually what's inconceivably hard to somebody like myself, which I think puts you in the realm of, one of the great polymaths, if you will, is that you were able to take many physical things and bring them together. And I think that is one of the things that I was also thinking, Dr. Stoker, is that the element of the polymath, in the sense that you had to integrate many disciplines into a single discipline, even within the context of the climate, because it ain't just wind, it ain't just solar, it's the gamut of all those, taking all those things and turning them into fluid dynamical models and getting them resolved seems to be an immensely non-trivial problem for somebody like myself. And I'm not sure that there's many. I think there's we need, there is an element there that it's like it's a pretty complicated, it's the integrating all of that understanding is what's most impressive, I think, about this invention.
Thank you, Eamon, and I'll tell you what what I am going to say is going to surprise you, perhaps. Being a mathematician or mastering that was the easiest part. Really, like I said, when I was 18, I was really on top of the world, mathematically speaking. But combining that with physical understanding, that's not an easy thing. So, if I were to describe my evolution, I was a pure mathematician. Nothing mattered. If you showed me a bolt and a nut, I wouldn't be able to tell which one would be which because I didn't really care. I would be able to solve, develop an equation for a bolt and a nut. That's about it. So my physical understanding was not something that I was entertaining. So I was a pure mathematician, and then I became a mathematical physicist because I was adding the physical understanding to my mathematical, I would say, capabilities. But in pursuing the physical processes more and more, I became more of a physical mathematician because the physics really overtook the mathematical capability.
And then you became a computer scientist because you had to basically then put it into a computer science model, and then you had to become a businessman to take the math and the physics and the computer and then apply it to real world problems. So I think that there's an evolution there, but it's coming from, because one of the things that is that there's this whole thing about the hammer and the nail. It's like you have to understand all of the tools of math in order to be able to select the ones that are the most relevant for the physical problem that you're trying to solve. And that's why I think coming from a pure math background is probably the best, because you have an understanding of this vast field of mathematics, but like that doesn't mean that all the math out there is of use as it pertains to solve or being of relevance to certain physical arenas. And that was the thing that I always struggled with most, was I was never quite sure whether this was the right math. It's math and it kind of maps to my problem space, but I'm not sure it is the math I should be using. And I think given your broad understanding of math, I think that probably helped you do some very innovative things, because physicists aren't always coming at it from a full understanding of the math. And I think coming from math to physics rather than from physics to math is probably a better way, given the polymath kind of. Would that be an accurate observation?
I think so, because the reason I started with math was because I didn't think physics was that difficult.
Right.
I thought it was easy. I just, could do it in my sleep, so I didn't really pay attention to it. But what I'm saying is, when you have that capabilities in math, and I would have to say I would add another point too. With my abilities in math, Eamon, I could probably create new math subject areas fairly quickly. But I don't see the reason why, although I could point out all the deficiencies in the existing mathematical branches, which is something that I do. So I don't really pay attention to, the mathematical knowledge, because you still have to be able to translate that to some physical systems.
Right, correct. So, so then getting back to our use case, to be a little bit more specific, and I apologize because I think I took us down this route of getting back to but I wanted the users to understand why this isn't NOAA. That was kind of the ultimate point. Is this is fundamentally a different service to what you're getting off of the current services, and then we can talk to now how again we use those in the context of the use cases. And I just wanted to make sure the users understood. This ain't NOAA. This isn't like a current service. It's a fundamentally different service. The math is different. The computation is different. The physical understanding is different. The integration is different. The resolution is different. And all of those fundamental things are different about the widget. And that allows us to do new and innovative things with the technology, correct? In the context of agriculture, in the context of energy, in the context of industrial policy, social policy, and maybe most importantly, in terms of climate change policy, which is now becoming a multi-trillion-dollar problem that all countries are facing. And that's one of the use cases, Dr. Stalker, I think is most interesting. Is we discussed the other day that countries within Europe and the world have got this Paris, they've got these targets they need to make, right? Which is reducing carbon, etc. How can your invention help somebody do a better job of meeting these international obligations that they have? So how would you suggest that, like in the Irish context, for example, how will this better help me get from where I am today, which is a very carbon intensive economy, to something that is, more economically viable, but also more ecologically viable? Can you just walk me through, maybe in the context of a couple of more examples of how you would see this invention helping a company even as large as even at the European level? How does this company help us jump across that leap across that chasm?
Well, that's a great question again. So, Eamon, one point I want to add to the evolutionary path that I was on, from the mathematics to physics. Not until I became a businessman, I did not dig deeper into my capabilities. So
okay.
I need to point that out, because my desire to give the best product to my clients actually made me do what I did. So all of the credit goes to my prior clients, current clients, and future clients, because that's what I was doing this for. Okay, so I want to point that out. It's not because of my research or my papers, those were fine, but I wasn't kicking myself deeper and deeper into understanding it until I became a businessman. That's when I needed to really put all of my abilities to do.
Would you say that is a little bit of the challenge of science, is that it stays in the ivory tower and it doesn't come down from the ivory tower to solve real problems in society, where that you're dealing with people? Is that kind of like is there a lesson there in terms of, like, yes, the science, knowledge and science and the right answers here, and solving real problems is here, and that there was still another leap you had to make to the point where you could have a service that could now be used to solve these fairly challenging problems. Is that
No,
a fair statement?
it is no disrespect to my colleagues that are not business people. In no way I'm just saying that, but when you are going to use your solutions to solve somebody's problem, real world problems, then you really have to dig deeper. So that's really what I'm saying. Where if you an accepted solution by 97%, let's take that example in the climate world, that's really not applicable in the real world, and that's when you stretch your company, get out of your comfort zone, and try to find better solutions. That's exactly what happened. In fact, this is no secret. I mean, every time I went to conferences, scientific conferences, I always used to tell them, bug them actually, you need to know about your clients, whether they're paying you or not. You have to think about that. And that's one of the reasons why, Eamon, I want to start Stalker Research Institutes across the world to bring that real world experience to research and then make the research efforts more applicable.
Right. So we have the tool. We've turned the tool into a service that can solve real world problems. Now what we need to do is operationalize that in the context of countries and in the context of real world use cases. So have you got a roadmap for the kind of industries and the kind of solutions, or are you operating like I've heard you speak to energy is definitely a core one, and you've spoken to agriculture, and you've just mentioned that this has got applicability to the general climate change arena of use cases. What is your talk to us a little bit about your how you see the problem spaces, and if there's any particular order or priority you have in terms of areas that you want to use your technology to apply problems within.
Okay, so let me answer your previous question too, and I will get to this. And I did not get to that. So you say I want to minimize my carbon footprint.
Oh, sorry. Yes.
As the chief of this natural resources division in Ireland. So I would say, okay, Mr. McCormick, if you install 1 gigawatt wind, that's going to offset your carbon footprint by so and so. Okay.
Right.
And that has to be not just in terms of what the estimated values are, but you have to be able to put that into the system,
right,
and making sure that system is actually producing those expected outcomes.
And that's where, just to bring it down to a personal level, my brother is a veterinary surgeon out in the west coast of Ireland, and his customers, the farmers, are particularly worried that there's talk about culling the herd, culling the dairy, the meat herd in particular, because of the climate impact associated with the dairy herd. And it seems to me like we really need a method of, it seems to me a little bit arbitrary to say, yes, I know that cows have got an ecological impact, but does it make sense just to start killing the cows? What makes sense here in the context of a country like Ireland to gigawatt of electricity, kill 100,000 or 500,000 cattle, or how do you trade off these things? How can your model help us make these kind of decisions?
Well, so
they're incredibly huge decisions for reducing the cow. I believe there's 2 or 3 million cows, or there's over 1 million cows in Ireland, certainly a couple of million. Reducing the herd is a pretty drastic step for the farming community.
I would say so. So what I would really help you specifically is when you invest up to 1 gigawatt in your wind, as an example, is that really producing the effect that you're expecting?
Right.
Right now, using the current science and the methods, you would not be able to ascertain that. That's really the bottom line, because those expectations are simple. They would say so and so much carbon is going to be offset if you have this, but there's no scientific way to make sure that actually happens until the Stocker method with the implementation in the RESPER model that would allow you to ascertain and make sure, or actually showcase to the world that it does happen. And the other side, the flip side of that too, Eamon, you might find that you could achieve the same benefit for half a gigawatt installation than 1 gigawatt. So that's savings too. Think about that. Your carbon offset is so and so X amount, but if you're doing it right and understanding all of the processes,
That's
you
true.
cannot actually have to have a gigawatt installation to achieve the same effect. And that's something that we could also help you with using the technology.
So one question there, and is that you've mentioned before, is the role of sinks, and that people don't really understand the role of sinks and you have sources and sinks in the atmosphere. Is that something that because that's another area that I'm particularly concerned about, is that if our models don't take that into account, we probably, like as you say, any model that we run would basically, it's a complex interaction, I guess, of processes here. And unless we have a model that can properly integrate all of those, I just don't know how it would work, because we would not be able to understand the relationships between the processes.
I can simplify that issue a little bit more,
Okay.
Eamon. So let's say there is a carbon source, let's say the cows.
Yes.
Okay. And you have sinks somewhere, like, the forest. Okay. And the source starts somewhere and the sink is somewhere else. How far do they have to be able to, take up all of the carbon that's being produced by cows? That type of analysis is not possible now using the current science, because of the limitations I talked about. So you might be able to estimate something, but it's not accurate. So that's why you need to be able to say, there is a source, but I have a sink. How do I manage them together? So that's some of the things that you could do with this robust modeling capability.
And I think the other aspect is pollution, obviously related to that, because that brings up the idea that, the atmospheric composition actually varies quite a lot. A few kilometers down the road, if you're at the center of town, there's a lot of sources of gas, different types of gases than you are uptown, or if you're in the suburbs. And I think if you don't have models at the resolution you're talking about, you will not be able to get any kind of a handle on locality as a driver of efficiency within these models, and I think that's an important kind of, I remember I visited a greenhouse once where the guy was growing tomatoes, and he was saying, oh, the tomatoes love the carbon dioxide, but like the carbon dioxide downtown may be quite different to the carbon dioxide up here. And it may not make a lot of sense to be putting carbon sinks where there's less carbon dioxide. So
resolution definitely is a big issue for the current science. So one of the points that I made in my presentation in Boston back in January was, when I made the analysis and compared with current methods, just from the error reduction capability standpoint, I was showing anywhere between 20 to 80% reduction or more. So that's how much I could knock down in the error that's inherent in some of the methods that are available to us now.
So from an Irish perspective, to what degree then out of the box can the service look like? In other words, how much of the service is kind of out of the box where I can just basically very reasonably rapidly do some modeling, and then how much work is it going to be for me to integrate these specific problems to a specific geography? Because I like
the cow thing is a rather specific to the Irish geography. Like each geography has its own unique localized. So how much localization is going to be required versus how much of the model is out of the box, if you will?
Well, one of the clarifications I wanted to make from our last conversation, Eamon, is the RESPER technology has 4 layers, as I was saying. Data production layer, which is a significant piece of it, but the other 3 layers are just as important because they're critical by the time it gets to you as the end user. Mm-hmm. So the analysis layer, when you have the data, you have to be able to analyze, but then you have to have the expertise also. That's another layer I talk about that goes into production layer as well as the analysis layer. But the point that you're making is the application layer. Now, for example, using the cows and the forests and their interaction, that's really an application layer. No matter what you do, you still have to go through the data production layer and the analysis layer in using the expertise to do the application. So applications are going to take time. So we will be recommending a list of things for you to do, mm-hmm. but you can prioritize whether that's air pollution that's driving your effort, or is it water resources or soil erosion or flooding. Whatever the case might be, you might have top 5 or 10 items that you want to tackle first. Although our list is going to be pretty extensive, it's really up to the customer what they want to tackle. And then we go into the application layer. And that's really where the research institutes can help some of the other folks I'm going to be engaging during that period.
Which makes sense to me. So therefore, we get a base sets of data. We can produce some basic services off that based on the analytics. But you really need to work with the local resources around the application layer and making sure that the applications are tuned to solving in priority order the problems for that particular local area. Even though there might be commonalities across areas around domains, there is a localization idea here because there is, there are, low problems tend to be local. Well, a lot of we have global problems, but I guess you could see them as just a summation of a bunch of local problems.
Absolutely, it's a spectrum of problems feeding one another, not only downscale but upscale too. So the effect could go from small scales to large scales and vice versa. So one of the points I wanted to make from the last conversation where you said, will we get the model? It's really not the model that you're going to get. You're going to get the data and the analysis capability and the expertise capability and the application layer capability. That's really what you all need to be able to address each and every one of your problems.
Correct. Okay. Yes, that makes perfect sense. So I'll have to. So I know you're in currently working with international agencies right now. Have you found it difficult for people to understand your method and then start to work this way? Or is it fair? Like, in other words, is there a big learning curve for people to start building these applications on top of the basic services? Or have you found there being a willingness to do that? Because I guess it's not, it's not maybe easy. Is it? Have you found? Because I know you're talking to some very large. You're working with some very large entities right now, and you have some experience in this. Is it a big hurdle to get people to work on the application end of the service?
It is, and I'll tell you this, and I used to talk about this a lot. We all use utensils in our kitchens and dining rooms, but we don't manufacture them. So, and the manufacturing wind data or climate data is the same. It's actually more difficult than manufacturing utensils. Yes. But that does not stop a lot of groups from having their own little teams, little computing and this and that. So they are not producing the best utensils that they need to have. So the point I'm trying to say is, even if they have access to the best data that we're going to produce, if you lack in your analysis capability and most likely in the expertise also in that department they lack, and the applications suffer. So that's why I'm saying to not only give my data to people, but also train them in the analysis capability and the expertise capabilities and the application capabilities through their research institutes first. But I will be willing to train anyone who is willing to help their countries, because ultimately that's what's needed. So, but would they be able to take the data and run with it? No, actually, it's not that easy. If it was, we would be having those solutions available to everyone by now.
Right, and I think that's the big idea is that it's going to take work, but it would be ridiculous to say that, you know, out of the box you're going to solve everybody's problems. You provide the invention, but there's still work to be done by other people to take do the analysis on and work through actually resolving the problems through the applications themselves. So I think any other answer would have been disingenuous, honestly.
Except for one end of the spectrum. Like, for example, you're a farmer, you have 100 acres or 200 acres, and you say, I don't know anything about the weather stuff. I don't really want to know anything about it. You give me the decision-making tools. So we produce the data, we do the analysis, and we do the application using our expertise and give them what they need. But that's really not the case for a countrywide effort.
And I think this is something that, you know, and I just want to just take it back up to 50,000 feet again. What we're essentially saying is that if you really need a physics-based understanding of reality if you're going to do good planning. And I know people they've got financial planning, they kind of understand that idea, and human resource planning and all this. But we're at a point in history where we've got to raise the bar now and look at physics and basically have a model of our physics and use that to drive our planning. And I think that's a huge paradigm shift, Dr. Stoker, which is that we're really suggesting that we have to have a science-based model of reality and use that science-based model of reality, at least in the context of the climate, which we all now are coming to understand isn't just a dumping ground for pollutions and gases and things. It's actually something that's important to us all, and to the life, that we have to get this, we have a tool, and we have to use that tool which is science-based so we can make informed decisions, science-based decisions. And I think that's something of a paradigm shift. We've been kind of flying blind a little bit. And no offense to anybody out there, but I think that's just where we've been as an historical species. And we're saying, hey, no, there is a possibility now to have a physics-based model that we can use to move the ball forward. And all large enterprises, all countries, they're probably the first set of users, but even down to the farmer, as we've said, or the individual householders, to be able to have services based on an understanding of the scientific processes, and then to use that to make informed decisions about your energy, you know, your health, your food, all of these different things are really kind of, it's a paradigm shift, and it's a whole new world.
Well, I tell you from one example, Eamon, when I was talking to somebody about using the RESPER technology for designing a renewable energy project. Well, they said, look, the methods that we're using, they yield results that are bankable, meaning banks accept them. And I said, okay, that's fine. But what if you take all of the props in that model where, you know, you have government incentives, local incentives, and a bunch of other things? If you take them all out, would the bank still be considering that bankable? The answer is no. So when you're propping something and you're making a project out of it and then make it bankable, that's one way that has been done. But here is when the technology and the physical understanding becomes
Yes.
so critical, when you have to deliver that power. You have no other alternatives. So your understanding is so critical in that, because you cannot say, well, if you don't have the energy, let's buy an insurance policy. That's not going to give you energy. It might give you
Absolutely.
some dollars, but it won't give you the energy that you need.
And it provides a physics that this foundation isn't going to change, because if the physics is decent or good, or the physics isn't going to change, like human policy changes, all of that changes, but physics we can rely on if it's proven out to be reliable, which your method has over the last several years. So we're actually building services on proper foundations as we go up. I fear, as you do, that a lot of the services we're building are based on a lot of assumptions or a lot of current kind of things that actually aren't going to hold. And that unless we build out our new generation of services based on fundamental understandings, fundamental truths, we're just essentially building on sand. And I think that could be, we could have a conversation about that across all industries. We have to go back to fundamental premises and build from the ground up, not rely on essentially assumptions that may not last, such as all the financial assumptions that the financial system works on. There's no guarantee that they're going to hold for the next 20 or 30 years. So I agree with you fully that we need to really, if this is a paradigm shift of building on solid ground, building on physical understanding, rather than what's a convention, essentially, because what's bankable, that is just a convention. It's not a reality, really. It's just a convention. And unfortunately, conventions saying, there was a convention for years that we'd make boats out of wood, so the guy making a boat out of iron would be deemed crazy. But
Right.
The physics of iron boats, the physics on that are good. And I really feel that that's another paradigm shift that you're suggesting, Dr. Stoker, is that forget conventions, work off of the known physical science, and you're in a much better place for building long-lasting solutions.
I appreciate that, Eamon. I actually used a phrase like elevated understanding in the context of weather modification efforts. So I used to use an analogy like, okay, imagine a river with two banks. And if you elevate your bridge over that water, you will be able to pass. But if you're trying to build a bridge underwater, okay, because you are not going to elevate your understanding, it's going to be costly for sure, and it's not going to be passable too at the same time. So that's really why elevated understanding
I love
is
that.
so critical.
Elevate the understanding and sense making based on things we can trust. And I think that's where we're back to this chaos of our society. The chaos of our society is because we're not having conversations based on realities we can all agree on. And that's partly because a lot of what we're talking about are social conventions, as you said, or tribal knowledge. We've got to get out of that and get back to fundamental knowledge and build rational solutions based on rational answers. And I know that many, it's like, this is the age of questioning, and it's a great age, Dr. Stoker, in the sense that this is a unique time for a unique invention like yours, because this is the optimal time. We're questioning things. We're questioning things now, and I think that's the optimal time for your invention, because your invention is about starting fresh from a new fundamental understanding. And I think, and frankly, getting way, way, way ahead of where we've been, but building on a solid foundation. And I think this is a unique time where people will be uniquely open to what you have to offer.
I believe so, Eamon. So one of my colleagues, a good friend of mine, she used to say, I don't have to name the name, but she used to say, you always take contrarian viewpoint about things. And I used to tell her, that's really not what I try to do. I try to find what's not there in the science. And unfortunately, because it's accepted by everyone else, it looks like I'm a contrarian. So I'm
Right.
not really looking at what's being done. That's not that exciting to me, but what's not being done, what I have to do. So every time I really put my mind to it, that's exactly what I do.
And one of the things that I'm particularly attracted to in these conversations, Dr. Stalker, is I am like lots of people just trying to make sense out of the world right now. And it's very hard to make sense out of the world. And by being able to come to these conversations and see that there is a way based on fundamental scientific understandings, based on fundamental mathematical understanding, based on fundamental science understanding, based on computational physics, based on computer systems, we can then move to a point where we can make decisions based on a more solid baseline. And that gives me the courage then to say we can solve our problems because we're building it off of a solid baseline. I feel that unless we take the step back to take the step forward, back to your point, we're making our decisions based on, I'm not confident in the decisions I'm making because I'm having a hard time sense making because there's so many things changing, which means that I think we have to create this solid base and off of that solid base move forward again, because otherwise we run the risk of we can't afford to make the big mistakes again. We have to make better, sounder decisions. And to do that, we need new tools and new approaches.
I do agree, and especially in the climate world. I mean, the urgency of it and our desire to solve it is there. And even if they politically mobilize the resources the needed to do it,
the worry is we'll watch it.
So long as you're using the old solutions, you're not going to be able to solve it.
And I think and I think with that sobering thought, I'm excited about continuing the conversations. We talked again at the very high level, and maybe hopefully the audience have a better grasp now of the fundamentals of world mapping. I think in the next few episodes, Dr. Stalker, you'd mentioned that you may be wanting to dig into some more specifics, maybe around energy or agriculture and some of the interesting work that you're doing with specific customers. So maybe that would be interesting to get more into the applied area next time, because I think hopefully now everybody kind of understands what world mapping is and why it's different and why it's a service and what the layers are. I think for lots of people out there, the application layer is going to be the one. If we can get them over the idea that it's different under the hood, now we can move into talking a little bit more in some of the next sessions about the application layer. Would that make sense to you as a next step?
It does make sense to me. Just one thing that I want to add from our last conversation, Eamon, I did say that, when you said you got extra satellite data, how would that work with the data that I create? So I wanted to kind of set some things clear there. I gave you data for this, say August.
Yeah.
And at the end of August, you have satellite data for the entire month. So satellite data in that case would be used for validation of how well I did.
Mm-hmm.
Of course, satellite data have their own issues too, but let's just say the satellite data are perfect for the sake of argument. Then my projected values are the predictions and the satellite data that you got. It's a matter of comparing one-on-one. You put it into an Excel sheet, 2 columns, get the difference and the error stats on that. So that's one application or use of your satellite data. So it's not affecting the data that I gave you, but it's helping you to understand how well it performed. So that's one. So the second piece is, if the available data are really of high quality, and I emphasize the fact that it's a big if it is the possibility, there are some situations where some minor corrections can be made to the forecast that I gave. So it's really another small percentage on a small percentage of error itself. So let's say 5% error and you reduce it by 2% on top of it. So that's a small percentage of error reduction you could do. So that's a second application of your site data, whether they're coming from monitors or aircraft or satellites, radars, or a combination. There is a third aspect to this also, Eamon. It's a big issue, but it also points back to what I was telling about enabling the underlying physical processes from the gradients in the state variables. So you would be able to improve those gradients if you have additional data, but that's really not a simple problem. It requires a lot of expertise and understanding at a very high level. So if you're able to, then it could also help from that perspective. But those are the three different ways satellite data could help with what I'm doing additionally.
And I think that's an important point that you mentioned the earlier, in one of our earlier ones, is that it's really all about the rate of change of the variables driving the physical processes that we should be looking at. And then anything that can help us get a better handle on that rate of change is a good thing, I would imagine. And I think that's a fundamental kind of the idea of change. Like, people tend to focus on the static number versus the rate of change is really what you should be interested in, which was new to me, probably obvious to your good self, but it was actually a very interesting.
No, it's actually new to the science, Eamon. So one of the points I actually
it's like, oh, that kind of makes sense, but
one of the points I made in my presentation in Boston was just that, enabling the physical processes based on the gradients.
Yes.
But what happens with the current methods is they are closing. I mean, this becomes a little bit more technical, but when you develop parameterization schemes to represent physical processes, you are closing them with the state variables, which is really what you're not supposed to do. And that's why I made a statement that current methods are invalid, scientifically speaking.
Right. Well, yes, and it's like, yes, it's, at least in my, and maybe this is wrong, Dr. Stoker, and forgive me if I'm wrong and correct me, but it's almost like they're calculating the wrong thing. You know, they're trying to calculate, and it's a bit like in computer science where you're modeling the output, you're not modeling the process. You know, you're trying to get to the output you're looking for versus modeling the process that creates the output and or that derives the output. And I think it's almost like you're completely missing the point. At least that's my understanding of what you're saying.
Well, I will elaborate on that a little bit more to Eamon, and that is, you already have small amount of data.
Mm-hmm.
And there may be some utility of the data, but
Yes.
because of the current methods, you're smearing that. You're actually blunting that usefulness of the small amount of data. That's how I describe when they're using models by closing with the state variables. So even if you have some utility of the small amount of state variable information, for example, the gradients, you're blunting their ability because of the approaches that are being used. So they're not even getting the full benefit of the available data that they could. And I'm, on the other hand, actually enhancing the usability of that using the process enabling capability.
And look, I'm just like Joe Blow in the street here. I understand that this is complicated stuff, and that I'm not a physicist or a mathematician, but it does seem like a pretty fundamental problem if we're not modeling the processes, we're modeling the outputs. That's, even I can kind of see that's that's probably a problem, and it's kind of like, don't you think
those who are scientifically,
it seems like a fundamental kind of gotcha, you know. It's like, and I can totally understand that
you know, it's super hard to model the processes. I get it, guys. It's super hard and it's much easier to do the other way. But bottom line is you know, unless you bite the bullet and model the processes, you're going to be off base. Okay.
Well,
yeah.
I'm also those who are scientifically inclined, and I'm also developing journal articles, so they will be able to understand some of the basics. So I
would love to do a Stalker method for the idiot's guide to the Stalker method. So if I can get it, anybody out there can get it, of how the Stalker method kind of works at a 101 level. I think that'd be a super thing for folks to start to get their heads around, because I know you did the presentation in Boston. I've watched it a few times. I've had to watch it several times, and actually it's almost like you got to take that and break it down into, okay, in those 10 seconds you said this, can we talk about that? And then in these 10 seconds you said this, can we talk about that? It almost feels like we have to take your Boston speech and break it down into, okay, can we just stop it right there and just get clear on exactly what you're saying? Because I've looked at it several times, I've watched it end to end, and it's kind of like, okay, for the layman, can we just break that down? Okay, stop. For the layman, can we break that down? And I think that would be a useful exercise, because it's a very profound. There's a lot of profound stuff going on there that I think you know, I personally would get a lot out of it, and then hopefully the viewers that are more interested in the under the hood of what the hell is Stalker method and what it really is and why this is a pretty profound thing. I think they'd get a lot out of it too, just to take that one lecture and break it down for the common folk.
I think that's a great idea, Eamon. So that was a scientific presentation. Yeah. So I was covering all of the bases, not only from the physical process standpoint, but the mathematical.
Well, in the first minute, there's a lot to talk about, and there's 15 minutes. So I'm sure there's probably 15 sessions just to get through that, but maybe we could simplify it a little bit for the folks out there, because I thought it was a good speech, and maybe we could use that as a, and maybe, you know, it's up to you, Dr. Stalker, but that's certainly a series of chats I'd like to have about the Stalker method.
I would love to, Eamon. So I will do as good a job as I can without resorting to the technical jargon.
Yes. So I'll just play the role of the idiot in the audience, putting up his hand saying, sorry, I'm the slow guy. Can you please explain what you mean by state variable? Like, so get all this
right.
stuff sorted.
And so I agree. And, you know, as a businessman, I learned to describe complex problems and complex solutions in simple terms, because I have to do that.
And in these sessions, I know I repeat a lot of things, but I hope that that's good for the users, because, you know, if they're like me, it takes a few times, takes repetition. It takes a while for things to burn into my brain. So I know there's a bit of overlap, Dr. Stalker, and maybe I'm going a little slower, but hopefully that works for the audience so that we can get everybody up to speed on all of the great things you're up to here.
I think so too, Eamon. I wouldn't worry too much about you know, going over the same material a few times, because, you know, as we know, those folks that actually produce videos professionally, they probably do tens, if not hundreds of rehearsals. The number of times we rehearsed is 0. So making
this is spontaneous stuff, guys. Yeah,
as natural as we could be, and that's really how I like it.
Yeah, and I really and I keep coming back to it because the fundamental thoughts are pretty profound, and I really appreciate your patience with me, Dr. Stalker, as we walk through these issues. Okay, I think that's it for today. We'll be back next week with another exciting episode of the Enterprise Universe, and more to come, but this is important stuff, and look forward. Please subscribe if you get a chance, folks, and thanks again to Dr. Stalker for giving us the time to explain climate modeling and climate mapping. Thanks so much, Dr. Stalker.
Thank you, Eamon. I appreciate it.